What is the VAE reparameterization trick? Imagine trying to teach a robot to create new images or sounds. It needs to understand the underlying patterns, but randomness makes this tricky. That's where the VAE reparameterization trick comes in. Variational autoencoders are a special kind of neural network that learns to generate new data that looks like what it was trained on. They do this by mapping input data into a smaller, simpler space called the latent space. Instead of just copying data, VAEs learn to describe the data as a probability distribution in this space. This means each point in the latent space can produce a different, but realistic, version of the data. The encoder part of the VAE doesn't just give a single point in the latent space. It predicts the mean and the variance of a Gaussian distribution. Think of it like saying, here's the average version, and here's how spread out the possibilities are. To generate new data, the model samples a point from this distribution and feeds it into the decoder, which creates a new data sample. Here's the problem. Sampling directly from this distribution involves randomness, and randomness makes it impossible for the neural network to learn through a process called backpropagation. Backpropagation is how neural networks learn by adjusting weights based on errors. But if the sampling is random, the gradients needed for learning can't flow smoothly through the network. This is where the reparameterization trick becomes a game changer. Instead of sampling directly, the trick rewrites the sampling process so that the randomness is separated from the learned parameters. It does this by always sampling from a fixed standard normal distribution, which is a simple Gaussian with a mean of 0 and a variance of 1. The sample from this distribution is then scaled and shifted using the predicted mean and standard deviation from the encoder. Mathematically, if the encoder predicts a mean mu and a standard deviation sigma, the latent variable z is calculated as z equals mu plus sigma times epsilon, where epsilon is a sample from the standard normal distribution. This way, the randomness is isolated in epsilon, which is outside the network's parameters. The rest of the process is now deterministic, allowing the gradients to flow back through the network during training. This trick is essential because it makes training VAEs feasible with standard backpropagation. Without it, the random sampling step would block the flow of gradients, and the model couldn't learn effectively. Thanks to this method, VAEs can be trained efficiently to generate new images, text, or other data types, making them powerful tools in generative AI. In the bigger picture, the reparameterization trick shows how clever mathematical techniques can solve practical problems in machine learning. It allows models like VAEs to create diverse, realistic data, which is used in applications like art generation, text synthesis, and even content automation. Understanding this process helps us see how advanced AI systems are built to handle the challenges of randomness and learning.